here's hopefully some revision on fractions. So a fraction is made up of two elements. These are a numerator and a denominator. And when we actually turn that into doing a sum, into doing the calculation, those are called a dividend, and the thing we divide a dividend by is called a divisor. The result of that is in a quotient. But the most important ones for today are the numerator on top of the fraction and the denominator on the bottom. Now when we add or subtract fractions, we have to have a common denominator. I know there's been a few bits of confusion around that in terms of whether it's divide or multiply. No. When we add or subtract fractions, the only way we can do that is with a common denominator, so they're out of the same proportion things. For multiplication, well, that's actually the easiest one. We just multiply a numerator by a numerator and a denominator by a denominator. So when we're multiplying two fractions together, multiply the top two numbers together, multiply the bottom two numbers, or in this case, as we're going to move on to today, letters together, and that's your multiplication. Division works very similarly, but if we divide one fraction by another fraction, we flip the second fraction, that divisor fraction, the fraction we are dividing the first fraction by. We flip it, and then we do a multiplication instead. So here are some examples of that. Right, addition and subtraction, again, we need a common denominator. So for example, here I have an equation. Well, I don't actually have an expression. Okay, 2x over 5x plus 4 over x. Now, I can't do anything with those until they have a common denominator, because the 2x is a description of out of 5x, and the 4x is a description out of x. So I'm going to get them to have a common denominator, and I'm going to do that by multiplying the fraction on the right by 5. I'm going to multiply top and bottom by 5. So that's going to give me 2x over 5x plus 5 times 4 over 5 times x. That gives me 2x over 5x plus 20 over 5x. And now I can add those two top pieces together and get 2x plus 20 all over 5x. Another example, x over xy plus x over y. Again, I can't do anything with these until I have a common denominator. So here, I've multiplied the fraction on the right, top and bottom, by x. Again, you have to multiply both the top and the bottom, both the numerator and the denominator, by the same thing. Otherwise, the proportions change and you've just changed the meaning of that fraction. It won't equal the same thing when you multiply it out. So I've multiplied the second fraction there, x over y, by x over x. Multiply top and bottom by x, and that's going to give me then x over x plus y plus x squared over xy equals x plus x squared all over xy. Now, multiplication. Again, in this case, what we do is we multiply the numerator by the numerator and the denominator by the denominator. This is actually the most easy, I think, operation with fractions. So, for example, here, if I want to multiply x over y by x over y, I just multiply the two together. X times x on the top gives me x squared, y times y on the bottom gives me y squared. So my final fraction is x squared over y squared. I want to multiply x over y by y over x. I can say actually that's the same as x times y over x times y. And of course, anything divided by itself is 1. So that's what I've got, equals 1. A slightly more complicated one now. X minus 1 over x minus 2 multiplied by x over y. I multiply the numerators together. I put x on the outside of that bracket. So I've got x, open bracket, x minus 1, close bracket, all over y on the outside of the brackets, x minus 2 on the inside of the bracket. And they're going to multiply both of those out. And that's going to give me x squared minus x on the top here, and at the bottom I multiply out this process to give me xy minus 2y. And then I'm really stuck. I can't do much else. I could, if I wanted to, split out this fraction and say it's x squared over xy minus 2y minus x over xy minus 2y, but it doesn't really help me do anything else at this point. But just to make the point that we can do that. We can split the numerator, keeping the denominator the same. It doesn't change the meaning of that information, and if you doubt that, put some numbers in there. Put numbers into x and y and see what happens. But one thing we can't do is ever split the denominator. So make sure you can realize that you can split that numerator up. So I've still got x squared minus x, and as long as I keep them over the same denominator, I don't change the meaning of that information. So a couple of examples of division. Again, we're going to use the same operation we use for multiplication, but first we have to flip the divisor fraction, the second fraction. So in this case, I've got x over y divided by y over x. I'm going to flip the second fraction, that's the fraction on the bottom there, the divisor, and that's going to give me x over y times x over y, which of course, just as we've just done, is going to equal x squared over y squared. Slightly more complicated one. X plus 1 over x plus 2 divided by x plus 1 over x plus 2. That second fraction, I'm going to flip it, and we're going to change the sum to a multiply. So this becomes x plus 1 over x plus 2 multiplied by x plus 2 over x plus 1. And that gives us this final result here. X plus 1, x plus 2 over x plus 2, x plus 1. Now I could at this point multiply out the brackets if I wanted to, but I've noticed something. Actually, we've got common things on top and bottom, and they cancel. Because x plus 1 divided by x plus 1 is 1, anything divided by itself is 1, I can eliminate that and give myself x plus 2 over x plus 2. But that's still two common elements on top and bottom. X plus 2 divided by x plus 2 is 1, because anything divided by itself is 1. So always keep a watch out for those, because they can be really handy to eliminate unnecessary sums. There is something else I wanted to remind you of for the fractions that I haven't gone over yet, and that's this. As with the linear terms, when we've looked at applying a power to things inside brackets, we said that we have to apply a power to all of the elements inside the bracket. So if we had AB inside brackets squared on the outside the brackets, that's the same as A squared, B squared. We have to square everything inside the bracket to get rid of the brackets. The same is true for fractions. Here I have an example. A over B in brackets to the power of x is the same as a to the power of x over b to the power of x. The only way I can get rid of those brackets is to make sure I apply the power x to every element inside the bracket. So for example, I've got some example here with numbers. I've got 4 over 2, all squared, so 4 over 2 inside the bracket, squared on the outside. And I'm saying that that is the same as 4 squared over 2 squared. And just to show that's true, I've developed that sum. So 4 over 2 is 2 squared. And on the right-hand side, 4 squared is 16. Divided by 2 squared is 4. And both of those, 2 squared and 16 over 4, is going to give me the same quotient, answer 4. The other section of today's mini lecture is transposition. This is about rearranging and changing formulae, changing equations. But we have to make sure that when we're changing them, we aren't changing the meaning. We have to make sure that they're still true to the original formula or expression we were first given. That means we do that by applying the same process to both sides of the equation every time. So we can add the same quantity to both sides, we can subtract the same quantity from both sides, we can multiply both sides by the same quantity, we can divide both sides by the same quantity, and we can square or apply a power, again, to both sides. But we always have to do both sides of that equation. So here's a simple example. I've got the equation x equals 5y plus 5. If I want to get y by itself, I want to do what's called solving for y. I want to solve for y and get y by itself. Firstly, I'm going to take 5 from both sides. So x minus 5 on the left, 5y plus 5 minus 5 on the right. We can then get rid of those 5s on the right-hand side here. Plus 5 minus 5, and that gives us x minus 5 equals 5y. But to get the y as just the y by itself, I'm now going to have to divide both sides by 5. So x minus 5 over 5 is the same as 5y over 5. And that's going to give me y equals x over 5 minus 5 over 5, which means y equals x over 5 minus 1. If you just want to, with the fractions there, I'm just doing exactly the opposite of what we did slightly earlier, and I've just put some numbers here to show that that is true. So if you're not sure about that working, have a look at those numbers, because it shows that that split of that fraction where I've kept the denominator the same, but I've split up the numerators, works, and I've done that because I can see that 5 divided by 5 is going to be 1, and that's going to give me an easier piece of information to deal with. It's going to give me less information, which is part of this simplifying process. So here's a simple example of transposition, which you've probably already used, and that's why I'm using it. I know you're looking at mole calculations as part of your lab work, so I'm using this as an example here. I've got the equation n equals small m over big M, where n is the number of moles, little m is the mass in grams, and m is the relative molecular mass. So I want to rearrange to enable calculation of mass. For example, or i.e., I want to solve for little m. So how do I do that? Well, I start with n equals m over big M. I'm now going to multiply both sides by the big M, because I want the little m by itself. So I have n times big M on the left, and m over big M multiplied by big M on the right. The ones on the right cancel. M over m is 1, and that means that I have little m equals n times big M. Here's a slightly different example. This is one from physics, and it's the equation for calculation of kinetic energy of an object. E equals half mv squared. So where E is the kinetic energy in joules, m is mass in grams, and v is the velocity in meters per second. So now I'm going to ask myself to rearrange to enable calculation of velocity, i.e. we're going to solve for v, solve the equation for v. So again, I'm going to start with E equals half mv squared. This time I'm going to multiply both sides by 2 to get rid of that half, because half is a slightly awkward number to be mucking around with. Multiply both sides by 2, and so I'm going to get 2e on the left, and the half disappears on the right, because the half multiplied by 2 is 1. I'm then going to divide both sides by that little m, because I know I want the v to be as lonely as possible, so I can work with it and get v by itself in the end. So I get 2e over m on the left and mv squared over m on the right. Those m's cancel, and we end up with 2e over m equals v squared. Now, you'll notice this isn't v, it's v squared, and I want to solve for v. So I have to square root both sides. There's a couple ways I can write that. I can write it like this. So I can say the square root of 2e over m equals the square root of v squared. Squaring square rooting anything that's squared obviously just gives us that value, v. So, v equals the square root of 2e divided by m. I could also, of course, have written the square root as to the power of a half on the outside of brackets. So don't forget that that is also a way that we write square root. There's a few things to learn about powers, also called indices. The first thing is that we write them like this. It's x to the n. X represents a number, n represents another number, and basically that notation means that it's the number x multiplied by itself n number of times. So for example here, you can see 3 to the power of 4 is 3 multiplied by itself 4 times. So 3 times 3 times 3 times 3, which is 81. There are a couple of other things you need to be aware of. Some little tricks we use. This is useful partly for numbers, but it's certainly very useful later on, and we'll look at it again when we look at algebra. We like to write a rule that is x to the power of m multiplied by x to the power of n is the same as x to the power of m plus n. Now again, we've got an example here, just to show that that's true. 3 squared, 3 to the power of 2, multiplied by 3 to the power of 3 is the same as saying 3 to the power of 5, so that's 3 times 3 times 3 times 3 times 3, which is 243. And you can check that out yourselves just to check it. The next rule I've got on here is to do with a minus n. So, x to the power of minus n is the same as saying 1 over x to the power of n. So again, the example we've given is 3 to the power of minus 4 is exactly the same as saying 1 divided by or over 3 to the power of 4, which equals 1 over 81, and that's 0.0123. Some other rules. This one's really quite similar to the other, but it's related this time to dividing powers by others. So, the rule is x to the power of m divided by x to the power of n is the same as or equals x to the power of m take away n. So again, the example is 3 to the power of 4 divided by 3 to the power of 2, and believe it or not, here we calculate it, 3 to the power of 4 minus 2, which equals 3 squared. And you can calculate that on your calculator to see if it's true. There are a couple of special cases. Here, x to the power of 1 equals x. Any number to the power of 1 is just itself. 5 to the power of 1 is 5. 7 to the power of 1 is 7. Anything at all. Again, try it on your calculators. The other special case is any number to the power of 0 equals 1. And that's quite useful if you're taking things away and end up with a 0 up here, for example. The final rule that you need to be aware of is x to the power of 1 over n is the nth root of x equals y. In other words, y to the power of n equals x, then x to the power of 1 over n equals y. again, the best way to test this out is to plug some numbers in and see how it works. Here we've got an example, 81 to the power of a half. A half is interesting. 81 to the power of half is the same as saying square root. That's a third or a root. They mean the same thing. And of course, they both equal 9. Again, you can try this out on your calculators. And just to prove it so, the rule above, 9 times 9, or 9 squared, is 81. So that does work both ways. Same here, 16 to the power of a quarter is 2. 2 to the power of 4, or 2 times 2 times 2 times 2, equals 16. Just keep putting some numbers in and see what happens, and you'll see it's true. So now we're going to talk prime numbers. Hopefully you've come across these in the past. A prime number is a number that can only be divided by itself and the number 1 to make whole numbers. Examples are on the board here, 2, 3, 7, 13, 19, anything that can't be divided cleanly, we'd say, into an integer or a whole number, unless it's being divided by 1 or itself. Now, using these, we can do something called factorizing, or factorization. Now, it says that factorization means write as a product. Now, I think you would have read last week that a product is the product of a multiplication. So, when we prime factorize or factorize things, we're going to split them up into the prime numbers that we multiply to get to that final number. So, I'll show you some examples. Here, we've been asked to factorize 84. 84 is clearly even, so I know I can divide it by 2. If I do that, I'm going to get 42. 42 is also even, so I know I can divide it by 2 again, giving 21. 21, I know my 3 times tables is divisible by 3, and that's 7, which is also a prime number. So to fully factorize or prime factorize 84, what I get is 2 times 2 times 3 times 7, which we can also write as 2 squared times 3 times 7. And it really does help here to know your times tables. So, there are some tricks to working out which factor you can divide into those numbers. The first thing I said, is it even? If it's an even number, you can divide it by 2. That's an easy one. The second, if it ends in a 5 or a 0, you can divide it by 5. So 5 is definitely a factor. The third rule is, do all the individual digits in the number, when you add them up, make a number that's divisible by 3. If that's true, then the factor is 3. I can show you an example in a sec. And the last rule that I'm going to tell you about is one for 7. With 7, it's slightly complicated. You take the last digit of the number, you double it, and then you take it away from the rest of the number that's left without that final digit. And if the answer is divisible by 7, and that includes 0, then that means that you actually have a number that 7 is a factor of. I'll give you some examples. So here I've got the number 18,954. If I add each of those digits up, 1 plus 8 plus 9 plus 5 plus 4, I get 27. 27 is divisible by 3, it's in the 3 times tables. So that means 3 is definitely a factor, and I can divide that by 3. I've also gone here with 259. Now this is the rule of the 7s. The way we do it to work out if 7 is a factor, we take that last digit, the number 9, and we multiply it by 2. And we take it away from the rest of the number, which in this case is 25. So 25 minus 2 times 9, which is 25 minus 18, and that equals 7. 7 is of course divisible by 7, so that tells us that 7 is a factor of 259. But what about when we get higher than that? What about, we can work out things like 9 or 7. Sorry, not 9. 9 is not a prime number. We can work out 3 or 7 or 2. That's quite easy, because those times tables are quite easy. But once we get to larger numbers, well, we have to look quite differently to see if we can work out if there are larger prime factors. Here I've done a table for you where I've got the product of each of the numbers in the top row and the side column. So for example, here 121 is 11 times 11. Down here 437 is 23 times 19. And you can use that then to look at the numbers you're left with if you can't see an obvious factor. Of course, in that scenario, you can also use a calculator as well to try and work out what the factors might be. So, the last things we're going to discuss in this mini lecture are highest common factors and lowest common multiples. So, here's the definition of the highest common factor, which we'll also call the HCF. The highest common factor is the largest number that is a factor of a set of numbers. So, let me show you what that means. Here, I've been asked to find the highest common factor and the lowest common multiple of 1020, 2652 and 7854. I'm going to start with the highest common factor. The first thing you have to do is take all of these items down to their primes, prime factors. So I factorized each of these numbers out. So the first one, 1020, I know I can divide by 2 because it's even. 510 I can divide by 2 because it's even. Then I can divide by 3, and etc., and etc. So having done that, I end up with 1020 is the same as 2 times 2 times 3 times 5 times 17. I then followed the same processes for 2652 and 7854. You'll get a chance to do this in your tutorials. To find the highest common factor, or HCF, what we do is we look at which factors are common to all 3 numbers. So here I've highlighted them. In all 3 of these numbers, when we've broken them down into their prime factors, we can see they all have 2, 3, and 17. You might ask why we haven't got 2 2s highlighted. Well, this number at the bottom doesn't have 2 2s in it. If it did, then we would certainly have that in there as well. But in this case, the only 3 common numbers between each of these things are 2, 3, and 17. That means that we calculate the highest common factor by multiplying those together. 2 times 3 times 17. That is the highest common factor. Have a look in your books, have a go at this. There's lots of exercises to get your teeth into in the core reading and exercises. The final thing we're going to look at is the lowest common multiple. Again, the lowest common multiple for a set of numbers is the smallest number into which all of them will divide. So this time we're not going smaller, we're going bigger. So to find the lowest common multiple, we have to again factorize each set. We have to take the highest number of each number of factors, and then we work it out using that, and I'll show you here. Here's a nice simple example at the bottom. I've factorized 2, 4, and 5. Obviously 2 is already a prime number, 5 is already a prime number, 4 isn't. 4, when you prime factorize it, is 2 times 2. So the factors here are 2 and 5. It doesn't matter on the number at the moment. Factors are 2 and 5. But now we have to count.
we have to look at what's the highest number of 2's that are multiplied in any single sum there. And if I look, well, that would be 2 2's. 2 2's is the highest number of 2's we multiply at any moment in that factorisation. In terms of 5's, well, actually, the highest number is 1 because it's only in 5. To calculate the lowest common multiple, we therefore take 2 2's and 1 5 and multiply them together. 2 times 2 times 5, giving the lowest common multiple 20. 20 is the lowest number that number 2, number 4 and number 5 can be divided into. Here's an example for the numbers we looked at earlier. The lowest common multiple of 1020, 2652 and 7854. Again, I've taken that factorisation that I did earlier. Up here you can see them, so 1020 is again 2 to the power of 2, or 2 times 2, times 3, times 5, times 17, and so on. Here, there's quite a few factors. There's 2, there's 3, there's 5, there's 7, there's 11, there's 13, and there's 17. And so this time I have to again look at what's the maximum number used at any time. Well, the maximum number of 2's used is 2. It's used in both 1020 and 2652's factorisation, but I've only highlighted one of them. 3 is used just once in all of them. 5 is used just once. 7 is used once. 11 is used once. 13 is used once. And 17 is used once. Now obviously it's in all three things, but the highest number that are used in any of those sums is 1 for everything but 2. So I calculate the lowest common multiple by multiplying 2 times 2 times 3 times 5 times 7 times 11 times 13 times 17, which gives us 1,021,020. And that's how you do one of the more complex finding of highest common factor and lowest common multiple. So first I need you to be familiar with a couple of terms that we're going to be using, and I'm going to be using these all the way through this lecture, so make sure you understand them now. If you need to pause it, if you need to remember them, make sure you do. So fraction, we have an example here. We've got 3 out of 4. Just here. This is an example of a fraction. It has 2 parts, a number at the top and a number at the bottom usually, although there are other kinds of fractions which we'll go through later. But generally, it will have a numerator, which is the number at the top, and a denominator, which is the number at the bottom. Make sure you're familiar with those terms. So, for example, in our fraction, in our 3 over 4, or 3 quarters, or 3 out of 4, we have 3 is the numerator, and 4 is the denominator. Now this is, interestingly, it's also the same as saying 3 divided by 4. So obviously we can calculate this out. And if we actually do that calculation, then we change the terms. The terms would be the dividend, in this case 3 would be the dividend, and 4 would be the divisor. The result of that calculation would be this. 0.75, and that's what we call the quotient. The result of the calculation from a fraction is the quotient. So there are different kinds of fractions. The fraction that you'll most often have seen probably before this is called a proper fraction. A proper fraction is where the numerator, here, number 5 in this case, the numerator is less than the denominator, or the 6. So where the numerator is smaller than the denominator, that's what we call a proper fraction. An improper fraction is where the numerator is bigger or greater than the denominator, such as this one, 6 over 5. 6, the numerator much bigger, well, not much bigger, a bit bigger than the denominator, and that makes this an improper fraction. Now, we can turn an improper fraction into a mixed fraction, and I've got an example here. So here I have 6 over 5, or 6/5, and I know that 6/5 is the same as saying 5/5 plus 1/5. The same as saying 5 out of 5 plus 1 out of 5. And that can be turned into 1 and 1/5, because of course 5 divided by 5 is 1. Now, quite often in science and engineering, we need to be able to add or subtract fractions. In order to be able to do that, we have to get the denominator the same. So you can't add 1 over 2 to 3 over 5 just by some quick method. We have to get the denominator the same. Now, just to remind you that different fractions can be expressed in many different ways. So, for example, here we have 1 over 2, or 1/2, and that is actually the same as 2 over 4, which is the same as 3 over 6. You put those things into your calculator, you're going to get the same result. The quotient will be the same. But when we want to add or subtract different fractions, we need to make sure that the denominator is the same, and that's what we call a common denominator. Now, to give you a little bit of insight based on what we did a couple of weeks ago, the lowest common denominator is the lowest common multiple of the denominators of all the fractions. So, if you need to remind yourself of what that is, if you need to remind yourself what the lowest common multiple is, you should go back and have a look at week 1. Now, there are a few different ways of looking at this. If you just want to add up a simple fraction to another simple fraction, there's a really simple way that we can do this to find the common denominator. For example, here I have 1 over 4 plus 2 over 3. I need to find a common denominator, and the simplest way to do that is to multiply 4 by 3 to get 12. The reason that works is because I know I can turn the fraction into a different fraction but with the same information, and I'll explain what I mean by that. We can change the denominator, but if we do that, we have to keep the fraction the same. It needs to have the same information in it, and that means that when you put it into a calculator, you need to get the same quotient out. So what we do is we multiply both top and bottom by the same number. So, first we were dealing with 1 over 4, a quarter, here. In this case, I want to multiply 4 by 3 so that I have a common denominator, 12. But to keep that fraction the same, I have to multiply the top by the same number. So I've got 1 times 3 divided by 4 times 3. Then I'm going to do the same for 2/3 here. But this time, I'm going to multiply both top and bottom by 4, the denominator of the other fraction. That means I end up with 2 new fractions, but they do, believe me, have the same information in them. 3 over 12 plus 8 over 12. Now, we can add those up really easily by just adding the numerators together. 3 plus 8 is 11, so 3 over 12, or 3/12, plus 8/12 equals 11/12. But what about if we have lots of fractions that we have to add or subtract together? Well, in this case, we can use what we learned about the lowest common multiple. Again, if you can't remember what that is, please go back to week 1 and have a look at it. In this case, we have a sum, which is 1 over 2 plus 2 over 5 minus 3 over 8. Well, how do we even start to approach this? We could do it the way I've just shown you. We could just deal with the first 2 fractions, change to the same denominator, in that case would be 10 using that method. And then once we had a new fraction for those first 2, then we could do it for the second fraction. But there is a quicker way, and that is to use the lowest common multiple. Just to remind you, to get the lowest common multiple, we have to get down to the factors of those individual numbers and then multiply them together to find our lowest common multiple. Now in this case, if we factorise 2, it's just 2, it's a prime number. And the same for 5. 8 is actually the only one we can prime factorise. And if we do that, we actually discover that we can divide it by 2, which would be 2 times 4, which of course is 2 times 2. So, factorised, apologies for that, it's difficult to write on this, is 2 times 2 times 2. So our lowest common multiple is going to involve the factors 2 and 5. And if you calculate that out, it's going to be 2 times 2 times 2 times 5, which is 40. So, I've determined that the lowest common multiple of these 3 denominators is 40. Well, now I have to convert those fractions. So how do I do that? Well, I do exactly the same thing. I have to look at how I keep that fraction the same. So if I'm converting 2 at the bottom here as the denominator of 1/2 to 40, how do I do that? Well, I've multiplied 2 by 20 times. So I have to do the same to the top of the fraction here. So 1 over 2 becomes 20 over 40. 5, the denominator of the second fraction, goes into 40 8 times. So I have to multiply the top of that fraction by 8 as well, and that gives us 16 over 40. For the third fraction, again, 8 goes into 40 5 times, so I have to multiply both top and bottom by 5, giving 15 over 40. Now you can see here that I can write it in this fraction either with separate fractions over the same denominator but separated out, or then on the next line I can actually combine these and have 20 plus 16 minus 15 all over 40. Again, if you want to check that with your calculator, you can, but that means the same thing. And again, it's reducing the amount of information we have to do. And if we want to calculate it out, it's reducing the amount of processes we have to follow. So, if I do 20 plus 16 minus 15, that's 20 plus 1, and that gives an answer of 21 over 40. Thankfully, multiplication of fractions is a lot easier. I do admit that adding and subtracting fractions together is a bit clunky. You need to practice that. Multiplication is actually a much simpler process. All we do to multiply fractions together is we multiply all of the numerators together up here, and we multiply all of the denominators together down here. So in this case, we have 1/2 multiplied by 2/5 multiplied by 3/8. At the top, we have 1, 2, and 3. We multiply all of those together, 1 times 2 times 3, which gives us 6. Then we do the same for the denominators to give us our new denominator. 2 times 5 times 8 at the bottom here, which gives us 80. that gives us a fraction 6/80. Now, you may well have noticed that that fraction can be what we call simplified. Simplifying means removing as much information as possible without changing the meaning. It means making things simpler. So here we want to reduce the numbers to the lowest possible value we can. It's a little bit like when we looked at factorising, but here, as long as we divide both top and bottom of the fraction by the numerator, both the top and the bottom of the fraction, the numerator and the denominator by the same thing, we can forget the information because the result or the quotient of that would still be the same. So here you can see we have 6/80, which has been simplified by dividing both top and bottom by 2 to 3/40. It's good practice to always take a fraction down to the lowest numbers we can. So if you can factorise those numbers and reduce it down, you should. And just to show you why that works, we can actually write 3 as a fraction. We could call it 3 divided by 1. And if we do that, then we have 1 times 3 at the top and 4 times 1 at the bottom. So it does still follow our multiplication rule, if you know that 3 is the same as 3/1. But don't get too mixed up on it. Just try and remember that if it's a whole number, you can just multiply the top number, the numerator, by that number. Okay, division. Actually, this is also pretty simple, but there's a trick to it. You have to know that dividing by a fraction is the same as multiplying by the flipped or inverted fraction. Again, you'll have to try this on your calculator if you want to understand it or see it, but I can give you an example here. For example, I have a sum 2/5 divided by 3/8. Now, in order to calculate that or to simplify it, I'm going to flip the 3/8 to 8/3 and change the sign from a divide to a multiply. So my new calculation is 2/5 multiplied by 8/3. That's a top-heavy or improper fraction. Now we just follow the same rule we followed for the other multiplication sums. So we multiply the numerators together, so we get 2 times 8 at the top. We multiply the denominators together, we get 5 times 3 at the bottom, which is 15. So we end up with 16/15. Now again, that's an improper fraction, so ideally what we want to do in this case is we can take it to be a mixed fraction of 1 and 1/15. Now this will be coming up again in a few weeks, but I thought we'd take a look at it now very quickly. We can actually apply powers to fractions in the same way we did to whole numbers last week. If you see a power applied to a fraction outside of some brackets like this, then it's really easy to get rid of that, to actually be able to calculate that out. All we do is it's actually the same as saying that we apply the same power to both the numerator and the denominator. Now, you might have to get a bit used to us using letters in place of numbers. In this situation, A represents a number, B represents another number, X represents a third number. Try not to get too confused by that. I'll give you some number examples now. There's another example below. Have a look at that if you like by pausing the video and seeing if you can check it with your calculator. top we have the number 123. Now we can write 123 like this. 1 times 100 plus 2 times 10 plus 3 times 1. Now, it's written in brackets to make it clearer, but obviously after the last couple of weeks, you know those don't need to be there. But if we multiply that out, we get 100 plus 20 plus 3, which is going to equal 123. So the pattern there is that this number here, number 1, we were multiplying by 100, and then the number 2, we were multiplying by tens, and as we moved to the right, we were multiplying the 3 by 1. But if we keep going to the right, beyond the decimal point, that pattern continues. There's actually a decimal point here, next to 123, but we don't write it because in this case there's no useful information beyond it. But if there were, the same pattern would continue. So for example, here I have 0.4, and I can write that as 4 times 1 over 10. Obviously, if I were then to continue that, I could write that as a fraction, which would be 4 over 10. The next example, 0.04. Well, I can write that again as 4 times 1 over 100. Again, that number getting bigger. I'm dividing by another 10 each time. So with each move to the right, we divide by another 10. That means that if we want to, we can actually split up a decimal when we have more information. So for example, here we have 0.456. We can write that as 4 times 1 over 10, plus 5 times 1 over 100, plus 6 times 1 over 1,000. So that's 4 over 10, plus 5 over 100, plus 6 over 1,000. And in that way, we split it into individual fractions. Then what we can do is we can convert them to the same denominator. We did this last week. So in this case, remembering that we have to do the same thing to the top and the bottom of the fraction so that the information remains the same. In this case, to get from 10 to 1,000, we have to multiply by 100. So that's what happens to 4 as well. It becomes 400 over 1,000. 5 over 100, well, that has to be multiplied by 10, top and bottom, to become over 1,000. So it becomes 50 over 1,000. And then 6 out of 1,000 is already out of 1,000. So then we can add those up simply, and we get 456 divided by 1,000. Then, just like last week, we can simplify. Now, you may find that you can go straight from here down to here. And that's okay. Here, if we look at the top number, the 0.456, we can see we are 3 decimal places beyond the decimal point. So you may just be aware that that is 456 divided by 1,000. So that might be the easiest way to convert that into a fraction. But then you still need to simplify like this. Here's some other examples like that. So here I have 0.104. Because I have 3 decimal places beyond the decimal point, that tells me that this is 104 divided by 1,000. Same number of decimal places, same number of zeros after that one. That's the easiest way to remember that. And then again, I have to simplify. So I take it from 104 over 1,000 to 52 over 500 divided by 2. I can divide by 2 again, 26 divided by 250, and then divide by 2 again, takes me to 13 over 125. 13, of course, is a prime number, so we can't go any further than that. But what about when we have zeros? Like this. So here's an example. We have 0.0104. Now, I'm going to use the same technique that I used in the version above. I'm going to count the decimal places. 1, 2, 3, 4. So I'm going to therefore write 0104, everything after that decimal point, which is divided by 10,000 with 4 zeros. Now, again, the smart ones among you may have noticed this zero isn't doing anything anymore. We don't have a decimal point to keep it after. It's just dead, so we don't need it. So that becomes 104 over 10,000. And again, we simplify and take it down to eventually get 13 over 1,250, and that's our fraction. So there's a couple of different ways you can do it when you're converting a decimal to fraction. You can take each section one by one, convert them to separate fractions, and then convert the denominator to the same and add them up. Or, if you're comfortable with it, you can use the number of decimal places and convert it into an over 1,000, over 10,000, over 10 fraction. And then simplify that. So percentage directly relates to what we've just been doing. Percentage means out of 100, and it means that we can express it either in this way as a percentage, or we can convert that to a fraction per 100. We can also use this to produce a decimal. We divide the percentage by 100 to calculate a fraction or decimal proportion. And then we can also multiply a decimal or a fraction by 100 to calculate a percentage. So here's a simple example. Here we have 12.3%. If I write that as a fraction around that model, I can write 12.3 per 100. If I then calculate that, I get a decimal, which is 0.123. I can do it backwards as well. I could take the decimal, 0.123, and I can convert it to a fraction. Now, I might actually want to do 123 over 1,000. Excuse me while I try and write that. Not the easiest with this. But then that's a really easy fraction to convert into a percentage, because I just knock that off and put a decimal point in there. And that becomes 12.3 over 100. Equally, I can get directly from this decimal here to this percentage here by just multiplying by 100. 0.123 becomes 12.3%. But it's really important you always include the percent figure or the percent symbol with that so that you don't lose information. Otherwise you won't know it's per 100. So here's another example. If I want to calculate 12.5% of 800, there's actually a few different routes that I can use to work it out now. First, I know that 12.5% is the same as 12.5 over 100, and all multiplied by that 800 again. So what do? Well, I could just calculate it with long division, or with my calculator, I can just do that sum and work out that 12.5 divided by 100 is 0.125, multiplied by 800. Then I could calculate that again. But I could also do this. I could say, well, okay, if it's 12.5 divided by 100 times 800, I know that I can just multiply by that number above the 100. So 12.5 times 800 all over 100. Then what I've done here is I've realised, well, hang on, 800 is 8 times 100. So actually, I can just get rid of that 0, and that 0, and that 0, and that 0. And that becomes 12.5 times 8 over 1, or 12.5 times 8. But I could also do it another way. The 12.5, the decimal might confuse me a bit, so I could, if I wanted, convert it into a fraction that made more sense. I could instead have 125 over 1,000, converted from that 12.5 over 100. It would still then need to be multiplied by 800. But again, I could cross off some of those zeros. I've now got 125 divided by 10 times 8. Again, I can move that 8 up above the 10, just like we looked at with fractions last week. And I could calculate that 8 times 125 is 1,000. So the final thing is 100. So there are multiple ways I can get to that final answer, and all of them are fine because they're mathematically correct. As long as whenever I'm doing a fraction, I am working with the same, I'm doing the same to the top and the bottom of the fraction, except where I'm multiplying by a whole number, like this. Then everything's fine and it will all work, and it should go to the same place. But this section here, 12.5 over 100 multiplied by 800, should be your starting point to work out a percentage of that value. So again, just to get you used to the idea, here I've got 0.1. I can also write that as 1 over 10. I can write it as 10 over 100 because I multiply both top and bottom of 1 over 10 by 10 to give me 10 over 100. And now I know that 10 over 100, or 10 per 100, is the same as 10%. Equally, I could just have multiplied that number by 100 to get to the percentage. Again, to convert a decimal to a percentage, you multiply by 100. So here are some other examples. 0.23 decimal, if I want to convert that to a percentage, is 23%. Slightly more complicated, 0.567 as a percentage, multiplying by 100, I move that decimal place 2 points, and I get 56.7%. Again, remember to keep that percent if you're doing this method. The final example I have is 1.34. If I multiply that by 100, I get 134%, and equally, that is possible. In engineering, when you're doing comparative things, or science, when you're trying to work out percentage increases or decreases, you might well end up with a percentage greater than 100. That just means it's 134 out of 100, so it would be a top-heavy fraction. So ratios are slightly different. They're another way of kind of expressing fractions. So here's an example. If we have a number of widgets and they need to be divided up in a ratio x to y, note the notation there, we use these two small dots in between the x and the y, then the total number of widgets is represented by x plus y. We then, for x and y, can come up with two fractions that we'll be using to calculate a final value. So here, our x fraction is x divided by x plus y, and our fraction represented by this for y divided by x plus y. I'll show you in numbers what that means. So here, I have 10 litres of water. And I need to split that between a container A and container B in the ratio 1 to 4, respectively. If you don't know what respectively means, that means in that order. So it's container A, that ratio is 1, and container B to 4. So if I want to calculate how much I'm splitting that 10 litres of water into for each container, I have to produce a fraction. And I do that like this. For fraction A here, I take this number, which represents A, and I put it on top of the fraction. And then at the bottom of the fraction, I add both those numbers together, just like on the slide before. So we have effectively x over x plus y, where x is 1 and y is 4. Don't get freaked out by the algebra, I'm just trying to get you used to it. That makes the fraction overall for A 1 over 5. For fraction B, we do the same thing, but for the other number, number 4. We take the 4, we put it on top of the fraction. So the fraction for B becomes 4 over 1 plus 4, because we have to include both of those numbers in the denominator. That makes the fraction for B equal 4 over 5. So how do we use those, though, to then calculate our litres of water? Well, we multiply them by the total. That's why we use the total numbers in the first place from this ratio. So, volume A, we know is going to be 1/5 of 10 litres. So here, I've got 1 over 5 times 10. That equals 1 times 10 over 5, which equals 10 over 5, which equals 2 litres. For volume B, that goes into container B, I take the fraction for B, 4 over 5, and multiply it by 10. That becomes 4 over 10 divided by 5, which becomes 40 over 5, which equals 8 litres. So now I have the split 10 litres in the ratio 1 to 4 for containers A and B. So here's another example. Bill and Ben are doing a job share. They work hours in the ratio 3 to 2. So Bill was first, Ben was second. The ratio is 3 to 2. So Bill's number in that ratio is 3 and Ben's is 2. The working week is 37.5 hours. How many hours does each work? So again, we need to form a fraction out of this from that ratio. We know that Bill is represented by the number 3, so that goes on Bill's numerator here. The total is 3 plus 2, that represents the total amount of work. And then it's all multiplied by 37.5 hours. That equals 3 over 5 times the 37.5, which if we multiply out is 22.5 hours. Then we do the same for Ben. The numerator is formed by the 2 from the ratio that represents Ben's work. The denominator is the sum of both of those ratio numbers. And then we multiply that fraction by 37.5, the total number of hours that they can work. We then calculate that out. It becomes 2 over 5 times 37.5, which equals, if we calculate it out, 15 hours.
be solving linear equations. Now, these are equations that contain a mixture of numbers and an unknown to the power of 1. So there's no squared or cubed in here. We're just doing a standard linear equation with one unknown and some numbers. Now, the way we approach this is to group all the terms containing the unknown, for example, x on one side of the equation. We group all the terms containing the numbers on the other side of the equation, and then simplify both sides to solve the equation. Here's a simple example. We have 2 open brackets 5x minus 4 close brackets equals 3 open brackets 6 minus x close brackets. The first thing we need to do is just follow the standard BIDMAS process or BODMAS process. We deal with the brackets and multiply those out. And that gives us 10x minus 8 equals 18 minus 3x. Multiplying everything on the left inside the bracket by 2, multiplying everything on the right inside the bracket by 3. So next I'm going to add 3x to both sides. So 10x plus 3x minus 8 now on the left equals 18, because minus 3x plus 3x, those two cancel out, and leaves us with just 18 on the right hand side. Next, I'm going to do the same with the numbers. I'm going to add 8 to both sides. So 10x plus 3x equals 18 plus 8. So that gets rid of my minus 8 on the left hand side because we've added 8 to that, leaving 0 in terms of numbers, and we're adding 8 to the right hand side. Then we simplify. So 10x plus 3x is 13x, and 18 plus 8 is 26. Now we divide both sides by 13. So that means that x equals 26 divided by 13, which equals 2. One more example. 3 open brackets x plus 12 close brackets equals minus 5 in brackets multiplied by 4 plus x. Again, we're going to multiply those out. So 3x plus 12 with the x plus 12 in brackets becomes 3x plus 36 equals minus 5 times the 4 is minus 20, minus 5 times the x is minus 5x, giving us 3x plus 36 equals minus 20 minus 5x. This time I'm going to add 5x to both sides. That becomes 3x plus 5x plus 36 equals minus 20, and that minus 5x has gone because we've added on 5x. Now we're going to subtract 36 from both sides because I want all the numbers on the other side of the equation, the opposite side of the equation, to be x's. So I've subtracted 36 from the left-hand side, which leaves just 3x plus 5x, and I've put that onto the right-hand side, so we now have minus 20 minus 36. We simplify, so 3x plus 5x is 8x, and minus 20 minus 36 is minus 56. Now again, we're going to divide both sides by the number applied to that x, by the factor or the coefficient next to the x. So x equals minus 56 divided by 8, which equals minus 7. But sometimes we're going to have more than one unknown. So how do we deal with those? Well, we're going to look at solving those issues with simultaneous equations. So simultaneous equations contain numbers and multiple unknowns. But to solve them, we need as many different equations as there are different unknowns. So for example, if we have x and y unknowns, we need at least 2 different equations to solve those. We do a number of processes. We perform what's called operations to those different equations. We can add or subtract whole equations to others. We can multiply or divide a whole equation to change it. And again, we have to do everything to both sides. Or we can substitute one equation into another. Here are 2 simultaneous equations that we're going to use. You can see both x and y in them, and some numbers. I've got equation 1, which is 3x plus y equals 8. I've put the number 1 in brackets to signify that's equation 1. And we've got equation 2, which is 2x minus y equals 7. Now, handily here, we have a plus y and a minus y, and that means that we can do something called solving by elimination by adding the two equations together. So I'm going to do equation 1 plus equation 2. So here I've got 3x plus y plus 2x minus y equals 8 plus 7. So I've added all the letter sides of the equation to all the number together, and I've added the number sides of the equation together as well. Now, I've got a plus y and a minus y, so those cancel out, those disappear. So I can simplify that down to 3x plus 2x equals 8 plus 7. I can simplify that again, and that's going to give me 5x equals 15. In this case, I've labelled it equation 3. I'm going to divide equation 3 by 5. So again, I'm going to have to do that to both sides. I have to divide 5x by 5 and 15x by 5, and that gives me x equals 15 over 5, or x equals 3. So now I have a value for x, but I still don't have a value for y. So I need to go back and I need to substitute x into the first equation. To be honest, it doesn't matter which you use. I'm going to use equation 1 this time because y is positive there, otherwise I'd have to do some strange rearranging. So here I'm going to put 3 back into x. So now rather than having 3x plus y equals 8, I've got 3 times 3 plus y equals 8. Take that down, 9 plus y equals 8. So I subtract 9 from both sides, giving me y equals 8 minus 9, which equals minus 1. And that gives me the value for y. So now I can say at the end of my my solving that x equals 3 and my y equals minus 1. And it is always nice to put that at the end so that anyone who's marking it can see it, and so that when you need to use that information, you know where that information is and it's nice and clear. Here are 2 more simultaneous equations. Again, we've got x's and y's on the left, and we've got numbers on the right. Equation 1 is 2x plus 5y equals 9, and equation 2 is 6x plus 7y equals 21. Now this time, we don't have the same number of x's or y's, because we can't do any kind of additional subtraction on that. Not yet, at any rate. What I'm going to do is I'm going to multiply equation 1 by 3. I'm going to multiply everything in 2x plus 5y equals 9 by 3. That's going to give me 6x plus 15y equals 27. And I've labelled that equation 3. Now, I do have the same number of x's that I can use. So in equation 2, I've got 6 x's, and equation 3, I've got 6 x's. So now I'm going to take away equation 2 from equation 3. So I've got 6x plus 15y all in brackets, minus 6x plus 7y equals 27 minus 21. Again, with this, always be careful of those negative signs. So when I multiply that out, I've got 6x plus 15y minus 6x minus 7y equals 27 minus 21. The 6x minus the 6x disappears. 15y minus 7y is 8y. And 27 minus 21 is going to give me 6. So I've got 8y equals 6. So y equals 6 over 8, or 3 over 4, which is also 0.75. I don't mind if you're going to use the fraction, or if you're going to use the decimal. If you're going to go on and use it in algebra, sometimes it's easier to use the fraction, but either one will work. Again, now we need to go back and we need to substitute in our value for y into the first equation. So 2x plus 5y equals 9, 2x plus 5 times 3 over 4 is 9. I've done it in fraction form, so 2x plus 15 over 4 is 9. I'm going to take 15 over 4 from both sides. I've developed the fraction here, so I've turned 9 into 36 over 4 minus 15 over 4. And that equals 21 over 4. But that is still only 2x. 2x equals 21 over 4. I have to divide both sides by 2 to get the value of x. So x equals 21 divided by 2 times 4, which is 21 over 8, or 2.625. Another type of equation we'll look at this week is a quadratic equation. Now, we've already explored quadratic expressions. Those are expressions in the form ax squared plus bx plus c. If we add an equals 0 onto that, so the form is ax squared plus bx plus c equals 0, that is a quadratic equation. Now, you might hear people, including me, sometimes mixing up the terms expression and equation. I'm sorry if that happens, but if it has an equal sign and there's something on the other side, that's an equation. So obviously this could be written slightly differently. It could be something like ax squared plus bx equals minus c, and we would have to move the minus c to the left-hand side by adding c to both sides. But if we can write it, ax squared plus bx plus c equals 0, that's a quadratic equation. Obviously, a, b, and c could be any number in this scenario. To be a quadratic equation, a must be, cannot be 0, but b or c could be 0, but it has to have an x squared there multiplied by something, 1 or something else, to be a quadratic equation. We've solved those just as with the linear equations by finding the value of x. But the important thing to remember is that quadratic equations have 2 solutions. So we call these the roots. The reason being, of course, if we root x squared, we can get back to x. So x times x would be x squared. But of course, we also have minus x times minus x equals x. So, for example, here we have at the bottom 16. We can get to that by multiplying 4 by 4, but we could also get to it by multiplying minus 4 by minus 4. So when we write root 16, the third, we can say that that equals plus or minus 4, which we write like this.
So, another basics relating to the trigonometry is the definition of the trig functions. Again, this is something we reviewed last year again. So we have these 4 or 3 basic functions: sine, cosine, tangent, or even you can consider cotangent as well as another basic trigonometry functions. And it all defines in a triangle. So every time you have a triangle, right angle triangle with the 90-degree angle inside, you could define this 3 side. You could define hypotenuse, and then for any angle inside this triangle, you can have adjacent and opposite side. So sine, the definition of the sine would be opposite over hypotenuse, or cosine would be adjacent over hypotenuse. Tangent would be opposite over adjacent. And cotangent is just the reverse of the tangent, which is adjacent over opposite. So you could define these two basic functions, and from there you could try to calculate these three functions, and later you're going to see what's the purpose or what's the function of these three functions, how we can use them in engineering problems, and why we deal with this kind of functions in the first place. So let's go through some of the example here. Like in a triangles, for any triangle, you could define these three functions for different angles, and here's the two examples. So we have equilateral triangles. Equilateral means there is two sides of the triangle which are equal. Here's an example of it. So we have this triangle with the two sides of two unit lengths. So we call this equilateral. And if I want to define this trig function inside this triangle, and if I start by drawing the height of this triangle, so I'm not sure if you're familiar with drawing the height of triangle. So for any triangle, you could have many heights and many base. And defining this height and base is very useful for calculating the area of the triangle. And you have done this, I think, many times for several subjects in high school maths. Here, we're just going to use that concept to define some functions to calculate the sine, cosine, and tangent. Let's say here, for example, if I have this equilateral triangle, if I draw this height between the two equal sides, then I could come up with these angles 30 degree and 60 degree. And for example, if I write the sine of the 30 with the opposite over hypotenuse, which is 2, would be sine 30 half. Why we are bothered with this two triangle? Because this would help us to calculate the sum of the sine, cosine of the basic angles. So the basic angles would be the angles like 30, 45, 60, 90, 0. And if you remember in the foundation engineering mathematics last year, you were not allowed to use calculator in your exam. And that was the idea, to push you to learn how to calculate this sine, cosine, and tangent of these basic angles. And you could use these basic functions, definitions, to get a better understanding of the concept of the sine or cosine. Another example, if I want to use this equilateral triangle to find the sine or cosine of the 30, I could do that. So, for example, sine of the 60 would be opposite over hypotenuse, which is a square root 3 over 2. Or tangent of the 30 degree would be opposite over adjacent. So it would be 1 over square root 3. And if you rationalize these fractions, you would end up with a square root 3 over 3. Another useful triangle is this isosceles right angle with the side of the 1. So if I have the isosceles, which means the two sides of them are equal, and with the right angle in the middle, then the both of the angle would be 45 degree, and I could calculate the sine and cosine and tangent of the 45 using this triangle. The triangle is a very useful base for the understanding of the trig function and for calculating some of the basic angles. And here we see another way to memorize this sine and cosine of these basic angles. So again, 0, 30, 45, 60, 90. This time we're using the unit, the circle of units. And the way we're going to memorize this time is we're going to draw these 4 points on the x and y axis and the positive. And we're going to start with square root 1, square root 2, square root 3, square root 4 divided by 2. Now, this would be 30 degree, this would be 45, this would be 60. So if I want to write the sine 30 now, what I'm going to do is, I'm going to look at the y-axis, so it would be half. Cosine 30, I'm going to look at the x-axis. Would be a square root 3 over 2. 60, again I'm going to follow this line, and this would be cosine, this would be sine. So sine. Another part of the understanding of the trig function is sketching them on XY chart. Last week we learned about the functions, and if you remember, we learned how to sketch linear functions, how to sketch quadratics, how to try to find the minimum and maximum of the higher power of the x, like a cubic functions. But for the trig functions, again, we could apply the same rule here. We could come up with a table of the values like we did here, and we give it some values, and you find the x and y coordinates, and then we connect those points to form the sketch of the sine or cosine or tangent. For the sine, we usually have the input as angles. So the angles, this unit of this angle could be degree, could be radian. So you have to be careful about what unit you're using. And in your calculators, again, you have to be, you need to know that how to input this in degree or radian. Usually in your calculator, there is a symbol on top in the screen of the calculator which says D or R. So D would be your unit of the angles in your functions you're going to input would be degree, and R would be radian. In this example, let's see if I try to input this value. So sine 0 is 0, sine 30 degree in half, 45 degrees square root 2 over 2, and sine 60 is square root 3 over 2, and 90 is 1. And for trig functions, we are talking about this periodic sort of functions, where we have two concepts here. We have amplitude, and we have the wavelengths. So wavelengths would be the point from which the sine is going to repeat itself. So for the sine x, the wavelength is degree, which means if I start by sketching the functions, the function is going to repeat itself. So I'm dealing with this unit of the sine or cosine with the wavelengths of the 360 degree. So the wavelengths would be from the point that the function is repeating itself. And the amplitude would be the maximum y or maximum height of the functions. And for sine, we all know that the sine never exceeds 1. So sine function is always between -1 and +1. So 1 in this example would be the amplitude of the function sine x. So all I need to do for sine x to find some points between 0 and 360, or between 0 and -360, or between 360 and 720, and then I can just copy paste that unit and place it side by side to have my sine x sketch for the infinity, minus and plus infinity. You can do the same for other functions. So for example, if you have a calculator, you could try this now. That the sine of the 270 is -1, and sine of the 90 is 1. Let's look at this one. So every time you have a coefficient in front of your trig functions, all you need to do is to multiply your amplitude by that number. So if I have y sine x, and if I want to sketch y equals 2 sine x, all I need to do is to multiply the amplitude by 2. So the maximum number, or the maximum height, or the maximum y point of my functions now is going to be 2 times 1, 2 instead of 1. So that's going to be the main difference between the sine x and 2 sine x. But the wavelength is still the same. So wavelength still is 360 or 2 pi. So makes my job very simple, right? So if I know how to sketch sine x, which is always going to be starting from which is always going to be between 0 and 360, and I could just use 90, 180, and 270. So it's always going to be this form. So if I sketch the sine x, now I can sketch the 2 sine x, 3 sine x, or any coefficients in front of the sine, and that would tell me the sketch of the 2 sine x. So 2 sine x would be simply multiplying the amplitude by 2, 3 sine x, half sine x. So that would make my job very simple if I want to sketch 2 sine x or any other. What if I have a number inside the sine? Let's say I have y equals sine 2x. This time the number 2 is inside the sine function. In this kind of example, the amplitude wouldn't change. Amplitude is still between -1 and +1, but the wavelength changed this time. So wavelength this time would be 2 pi over 2 or pi. As you can see in the sketch here, what happened here is the sine x, my wavelength was 360. But for the sine 2x, my wavelength is 180, which means the blue one, the blue sketch here, is being repeated after 180. So from here, I reached the same point here for my blue one. So what's happening here is my amplitude is still 1, it's not changing, but the point that it's reaching to the 1 is changed. So when it was sine x at 90, it reached the point 1. But for the y equals sine 2x, at x 45, I have y equals sine 2 times 45, or sine 90, which is 1. So this time, I'm reaching to the point 1 at 45. Last time, I was reaching at point 90. So amplitude is still the same, it's just the point it reaches this maximum point change from 90 to 45. Let's do another one, cosine x. Again, if you draw the table of the values and find the values of this number, again, the number we are selecting, the angles we are selecting in this table of the values, is kind of, we are choosing the one which is the basic angles, which is 30, 45, 60, 90. But after that, I'm just going random here, right? So I'm just going 120, 135, 150. Again, it doesn't really matter, it's just about the simplicity of finding the value of those parameters. So cosine 0 is 1. Again, you could use your calculators to find the value of this y for the range of the theta. So as you can see here, the amplitude still is 1. So the amplitude is still 1. But the wavelength now is still the same. Wavelength is still the same as 360 or 2 pi. My amplitude now is 1. But the starting point is different, right? If I want to start and draw the sine here, sine was 0, 0, at 90 it was 1, and then at 180 it reaches 0. At 270 it was minus 1, and at 360 it reaches 0. So you see the sine, this is sine, and if I want to draw the cosine here, this is cosine. So if you look here, if I take the sine and I move it to the left, so if I take this sine and move it 90 degrees to the left, that would be exactly like cosine. Or, in other words, if I take the cosine and take it 90 degrees to the right, that would be exactly like cosine. So what this tells us that sine and cosine are actually same function but with different phase. We call this a phase difference. So they have a phase difference here. And I'm not sure, but some of you are electrical, so you're familiar with the three-phase and one-phase currents. And that's kind of a main application of the trig function, actually, that it developed from the concept that you have different wavelengths. And again, it's in mechanics as well, it has applications. When you're dealing with a wave, and you have every wave has a certain wavelength, every wave has certain amplitude, and sometimes you have multiple waves running side by side on a stream, and you have a couple of phases, they are running in the different phases. So you have a phase difference. So we say the sine and cosine as the phase difference of the 90. And I think we have transformer, right? They transform from one phase to another, from single phase to two phase. Same applies for the cosine. If I have the number outside or inside the cosine, that would make a difference in the amplitude and wavelengths of the functions. So, for example, 2 cosine x has the same wavelengths of 2 pi, but the amplitude is 2 times 1. For cosine 2x, wavelength is 2 pi over 2, or pi. Amplitude is still 1. And sketching those functions, again, you have to be, so you can always sketch the cosine first. So cosine, I could just sketch the cosine, and then if I want to have sketch 2 cosine x, that would be, or if I want to sketch something shorter or longer, then I could easily do that. How about tangent? Tangent, the story is slightly different, because if you remember the basics of the tangent is opposite over adjacent, right? And we can even use the term, the fraction of the sine over cosine to calculate the tangent x. If I use the calculator to find the value of a tangent here, I could easily see, I could develop this table of the values for tangents, and if I connect these points to each other, that would give me the sketch of the tangent. The tangent of the 0 is 0, so here I made a mistake here. 0. Tangent of a 30 would be a square root 3 over 3. Again, I could try to use this formula here. Let me use this formula. So I don't want to use calculators. I want to use this formula here. So tangent 30 is sine 30 over cosine 30. Sine 30 is half, cosine 30 is square root 2 over 2. I do these calculations, these two cancel out. I'm gonna be 1 over square root 3 over square root 3 over 3. But tangent 90, I need to calculate tangent 90. It is sine 90 over cosine 90 would be 1 over 0, which is infinity. So you remember, any number divided by 0 is infinity. Function. So I'm going to see a sharp increase close to the point 90. Suddenly from 80 to 85 or 85 to 90, suddenly my number is going to increase sharply from 50 to maybe 1000 or 10,000 or an infinite number. And that's what's happening when you sketch this function. You can never sketch the 90 itself. You're always going to just get close to the line, but there would be a sharp increase. But again, if I start calculating 95, I'm going to see I'm getting a really large negative number, which is starting from really large negative number to 0. So the sketch of the tangent, as you can see here, I have the point 90, and it just goes up sharply. Another interesting thing about tangent, so amplitude in this case is infinity, right? There is no amplitude like a sine and cosine, but there's a wavelength. The unit, if I take from minus 90 to 90, I can just copy paste. I can just copy paste this one. So there is still a wavelength, there is still a period. So this time the period is shorter. This time the wavelength is 180 or pi. So if you remember from previous slide, sine, cosine, amplitude, 1 wavelength, 2 pi or 360. Tangent, amplitude, infinity, wavelength 180. Another useful rule regarding trigonometry is called CAS rule. And this is about memorizing the value of the basic trigonometric functions. So for any unit of the circle, I can write this CAS rule. And what means this CAS rule, or this letter CAST means? In that quadrant, so we call this one quadrant 1, quadrant 2, quadrant 3, quadrant 4. In that specific quadrant, the sign of the trig functions, you could know this sign before even calculating it. So if I place an angle in a certain quadrant, then I could tell you whether the value of the cosine, sine, tangent, or cotangent is positive or negative. So in the first quadrant, all cosine, sine, and tangent are positive. In the second quadrant, only sine is positive, hence the letter S. In the third quadrant, the value of a tangent is positive, that's why we have the letter T. And in the fourth quadrant, we have the letter C, which means the cosine is positive. Only the cosine is positive, so sine and tangent are negative. In the third quadrant, only tangent is positive. Sine and cosine are negative. So again, the sign of this trig functions, you could try to use this CAS rule. So it helps a lot. Like someone tell you, what's the sign of 120? So what I do is, I'm gonna go to here. So here is 0, 90, 180, and 270. So 120 would be somewhere here. So sine of 120 is a positive number. Cosine of 120 is a negative number. But besides these basic functions, sine, cosine, tangent, we have some secondary trig functions, which you might see their applications, again, because this is a level 4 math, we expect you to know about the secondary trig functions, not only the basic ones. So the second is one of these functions, and usually is the flip of the existing trig functions. So second would be 1 over cosine, cosecant would be 1 over sine, and cotangent would be 1 over tangent. And what's the use of having this extra trig function? So that why we just use 1 over cosine instead of defining a new function called secant? So again, there is an application in differentiation of the tangent when you have to deal with the 1 over cosine over and over. And it makes sense to define new functions to make your job easier. So in addition to this basic functions, we have some rules which is very useful with triangle. When we are dealing with triangle, because again, many engineering applications, you might be dealing with the forces, you might be dealing with the unknown lenses, you might be dealing with many unknown parameters. It could be defined in the geometry of the circle and triangle or angle in particular. And every time you're dealing with angles, trig function are useful tool for the calculations, for the determination of the unknown values. And we can use certain rules to find some of the values when there is a correlation. When you're dealing with triangles, there's always going to be some constraints imposed to one angle because of the values of the other angles. And we're going to use some of these rules to help us define this constraint and use those constraints to find the unknown parameters. The first one is sine rule. In a given triangle like this, when you have the ABC and the length of the sides is called ABC. So the length of the side A in front of the angle A is called lowercase a, and the angle itself is uppercase A. Imagine if I drew the heights for this triangle, and I define this height h. Now if I define the sine of the angle A, it would be opposite over hypotenuse. So now I'm just looking at this triangle. So it would be opposite over hypotenuse, h over b. And sine of b would be opposite over hypotenuse, which is h over a. If I rearrange this one by cross multiply, I'm going to end up with two equations for my h. So h would be b sine a, and h would be a sine b. So I have h, which is the same height for both sides of this triangle. If I equate these two h to each other, I'm going to end up with b sine a equates a sine b. Now if I divide both sides by sine a sine b, these two signs cancel out, so I'm going to end up with b over sine uppercase b equates a over sine uppercase a. So you could develop the same sort of equations for the other one, for the last one as well. And the overall rule, sine rule, says length of any side divided by the sine of the opposite angle, its ratio is constant for a triangle. So for any given triangle, you could write this sine rule, which means length of any side in triangle divided by the sine of the angle in front of it, that would be a constant ratio. And this ratio is constant for any given triangle. Okay, I'm going to give you a few minutes. I think you're tired of me talking now. So let's give it this exercise a try using the sine rule. let me write the sine rule here. So it would be A over sine, oops. So it would be A over sine A equals B over sine B equals C over sine C. So you have 30, 45, and the question asks you find the value of the sides of the A and C. Can you give this a try? I'm going to give you 5 minutes on this one. Okay, so I can look at this one, right, and I see 30, 45, and I look at the sine rule. It seems that the A could be a good start, right? So it would be A over sine 45, which is the opposite angle, equals 3 over sine 30. So if I rearrange this one by cross multiplication, I get A equals 3 sine 45 over sine 30. So it would be 3 times square root is 2 over 2 over 1 over 2. So if I again use far to far, close to close, I'm going to end up with 3 square root is 2. Which would be 4.2. Now that I find the value of the A, which is 4.2, for the C, I can again use the sine rule, but I don't have the angle in front of it. How can I find the angle C here?
Add 2.
Right? Because we have this rule in triangle, for any triangle, the sum of the angle is 180. So 30 plus 45 plus C is 180. So C would be 180 minus 30 minus 45. So if 30 plus 45 would be 75. So it would be 105. Now I can use the sine rule again, would be C over sine 105 equates 3 over sine 30. So if I write this again, would be 3 sine 105 over sine 30. Let's determine the unknown angles in the following triangle. So we have alpha and theta unknown, but we have 5 and 10 meter and 135. Can you give this one a try? I'm going to give you 2 minutes. 2 or 3 minutes. So what's the starting point here? I have 10 and 135, the angle in front of it, that's known. I have 5 meter, so obviously alpha would be a best start for me, considering the sine rule. So it would be 10 over sine 135 equates 5. Let me show you another way of doing it. So remember the sine rule, right? When we say the ratio is the same, when we say the A over sine A equals B over sine B, I could flip these fractions and it still is the same rule. So I can say sine A over A, sine A over A equates sine B over B. So in this example would be sine alpha over 5 meter equates sine 135 over 10 meter. So if I do this now, sine alpha would be 5 times sine 135 over 10, or sine alpha would be sine 135 over 2. if you calculate sine 135 over 2, you still you haven't got the alpha, right? You had this sine alpha. So to find the value of the alpha itself, you have to sine inverse it, or arc sine it. And you have this in your calculator as well, would be sine inverse of sine 135 over 2. So if you put this in your calculators, how much is it? Can you put this in your calculators? Tell me. Again, your output could be degree, could be radian, right? Let's go with degree here. Now that I have the value of the alpha, which is 20.7, I can find the theta by using the sum of the angles should be 80 fact, right? So it would be 180 minus 135 minus 20.7, and that would give me the value of the theta. So you get the idea. So using the sine rule, they have to see the unknowns and use the other rules, other facts on triangle to make your job simpler in finding the unknown parameter. Let's try this one, another one. So beside the sine rule, we have another rule. It's very useful again in finding the unknowns within a triangle. And here is the proof of it. Again, it starts by drawing the height of the example triangle, and this time we're going to use the Pythagorean theorem. So Pythagorean theorem, if you remember, when you have two sides and hypotenuse, you have that h squared equals a squared plus b squared. So we're going to use this concept here to prove that, I'm not going to go through the steps by steps of the proof of the cosine rule. Again, in the exam, obviously this is an open book exam in January. But again, if it wasn't an exam, open book, we would have given you the sine and cosine rule formula in the exam. But the concept comes from the fact that if you draw the height of the triangle, and if you use the Pythagorean theorem on the left and right of this triangle, and if you equate the value of the h in these two triangles, you're going to end up with this formula here, which says a squared equates b squared c squared minus 2bc cosine a. So in other words, what we are saying here is side of any triangle could be calculated based on the length of the other sides and the angle between the two other sides, or the angle of the opposite angle to the side. So if I want to find the value of the A, all I need is the C, B, and the angle A. And if I have these three other unknown parameters, these three B, C, and angle A, I can find the length of the side A with the lowercase a. So let's see it in the example here. And we could, so in other words, so if I want to find A squared, would be B squared plus C squared minus 2bc cosine A, and A is the opposite angle to the side where I'm trying to find the value of it. I could do this for the B, I need this angle, for the C, I need this angle. So if I have this value of this angle and the side on the two sides of this angle,
here's hopefully some revision on fractions. So, a fraction is made up of two elements. These are a numerator and a denominator. And when we actually turn that into doing a sum, into doing the calculation, those are called a dividend, and the thing we divide a dividend by is called a divisor. The result of that is in a quotient. But the most important ones for today are the numerator on top of the fraction and the denominator on the bottom. Now, when we add or subtract fractions, we have to have a common denominator. I know there's been a few bits of confusion around that in terms of whether it's divide or multiply. No. When we add or subtract fractions, the only way we can do that is with a common denominator, so they're out of the same proportion things. For multiplication, well, that's actually the easiest one. We just multiply a numerator by a numerator and a denominator by a denominator. So when we're multiplying two fractions together, multiply the top two numbers together, multiply the bottom two numbers, or in this case, as we're going to move on to today, letters together, and that's your multiplication. Division works very similarly, but if we divide one fraction by another fraction, we flip the second fraction, that divisor fraction, the fraction we are dividing the first fraction by. We flip it, and then we do a multiplication instead. So, here are some examples of that. Right, addition and subtraction, again, we need a common denominator. So, for example, here I have an equation. Well, I don't actually have an expression. Okay, 2x over 5x plus 4 over x. Now, I can't do anything with those until they have a common denominator, because the 2x is a description of out of 5x, and the 4x is a description out of x. So I'm going to get them to have a common denominator, and I'm going to do that by multiplying the fraction on the right by 5. I'm going to multiply top and bottom by 5. So that's going to give me 2x over 5x plus 5 times 4 over 5 times x. That gives me 2x over 5x plus 20 over 5x. And now I can add those two top pieces together and get 2x plus 20 all over 5x. Another example, x over xy plus x over y. Again, I can't do anything with these until I have a common denominator. So here, I've multiplied the fraction on the right, top and bottom, by x. Again, you have to multiply both the top and the bottom, both the numerator and the denominator, by the same thing. Otherwise, the proportions change and you've just changed the meaning of that fraction. It won't equal the same thing when you multiply it out. So I've multiplied the second fraction there, x over y, by x over x. Multiply top and bottom by x, and that's going to give me then x over x plus y plus x squared over xy equals x plus x squared all over xy. Now, multiplication. Again, in this case, what we do is we multiply the numerator by the numerator and the denominator by the denominator. This is actually the most easy, I think, operation with fractions. So, for example, here, if I want to multiply x over y by x over y, I just multiply the two together. X times x on the top gives me x squared, y times y on the bottom gives me y squared. So my final fraction is x squared over y squared. I want to multiply x over y by y over x. I can say actually that's the same as x times y over x times y. And of course, anything divided by itself is 1. So that's what I've got, equals 1. A slightly more complicated one now. X minus 1 over x minus 2 multiplied by x over y. I multiply the numerators together. I put x on the outside of that bracket. So I've got x, open bracket, x minus 1, close bracket, all over y on the outside of the brackets, x minus 2 on the inside.